So now we're going to be looking at floating point notation. And an easy way to look at this is scientific notation for a computer. So if we think about in engineering, we usually deal with very large numbers and very small numbers. And how we deal with those in an easy way is we use scientific notation. And like, for example, megapascals, 200 megapascals, you would say times 10 to the 6. And it's a lot easier to write that down than to write down the entire number. It's the same with the computer. If you wanted to convert a number like that, just think of capacitance, microfarads. If you wrote down that number, if you just wrote down that number, it's a big number, or it's a very small number. And if you converted that to binary, the number would be massive. I mean, you wouldn't be able to write down all the ones and zeros. It'll take so long. And storing that number in the computer would be inefficient, because it would take up so much data just to store one number. And then just consider if you performed calculations with that binary number, then it would be such a mess, and it would take up so much data, and it would be so slow. So we wouldn't want to do that. So what we do for the computer is, just like with us, we store those numbers in floating point notation. So what I have here is an example of what you could get. So I've left little spaces, if you can see here. If you look carefully, I've left just a little bit of space in between the different parts of the number so that you can see what they are. And they're going to do that too. So you must just get used to seeing it like that. And the first digit here, this 0, is the sign bit of the exponent. So the second 3 digits here is the exponent. And this digit over here after the exponent is the sign of the number, or the mantissa. So I've broken it up here. So you can see this 0 is the sign. These 3 digits over here are the exponent. This 1 over here is the sign of the number. And this is the actual number. So that's what we call the mantissa. All right. So I've separated it like that, so you can see it very nicely. And when you get a negative sign for the mantissa, what we have to do is we have to use 2's complement to complement the number. So let's do that. So we're going to write down 1. All right. So we write down the first 1. And then after that first 1, we complement the rest of the numbers. So it's 1, 1, 1, 0, 0, 0. All right, so there we've used 2's complement and we've complemented the number. All right, so here's the number now, or here's the mantissa. 2, 3, 4. Okay, and when it's in this form of floating point, the comma is always in the front of the number. So you can see over here, there's the comma. All right, so the comma was also over here in the front of the number. Okay, now once we got that, we look at the exponent and we say this will tell us how many positions the comma must float backwards. All right, so that number in binary, as we know, is the number 4. So we're going to move this comma 4 positions to the right. So 1, 2, 3, 4, and we're going to put it over here. Okay, so then we can write down the number. So it's all right, so that's the binary number, and that's all it is to it. And then we can just convert the number into decimal if we want to, or whatever other number system we want. So that's how we do floating point notation. Remember again, the exponent, the sign of the exponent, the mantissa, and the sign of the mantissa. If this is a 0, we wouldn't use 2's complement. We would just take the mantissa and we would know that the comma is in front of it, and we would float it back to where it's supposed to be. In this case, the exponent was 4, and we moved it 4 positions backwards.